Hello, good morning, everybody, and welcome to Papaling Physics Classroom. Okay, today we have been looking at the prelim paper for 2021 Springfield Secondary School. Okay, today the prelim paper that we are going through will be for the Sec 4 Normal Acad. Okay, Normal Acad paper is 1 hour 15 minutes, but it include paper 1 and paper 2 together. So which means paper 1 would be 20 MCQ question, then followed by your paper 2, which is 30 marks. Okay, so together you have a 50 mark paper in 1 hour 15 minutes. So if you look at the timeline, and I would say the NA paper is quite time demanding. So it requires the students to actually chunk out the answers, to understand the answers, okay, to write the correct answer, to choose the correct answer at a short time. Okay, so that's why it's a bit time demanding for students, but nonetheless it's a subject, it is a paper that actually it is a problem that can be overcome whereby you're looking at, like, if you have ample of practice and you know actually what the question is actually looking out for. Okay, now without delaying, okay, we will be looking at the Springfield Secondary School for an 2021 paper. Okay, if you have not done, if you have not seen the paper or you have not done, okay, the paper I've downloaded to my Google Drive. The link is in my description below, okay, in the description panel below. Okay, so you can download the paper and give it a try. Okay, so if you have done it, okay, I will be going through the answer for the question, okay, for the paper 1 and paper 2. So if you have done it, okay, you can take it out and actually look at the answer for now is for paper 1 MCQ. Okay, the 20 marks question, 20 MCQ. So if you are done, you want to take a look at the marking, you can pause the video here, okay, to check your answer. Okay, so without delaying, okay, we will look at all the 20 questions, and to see what are the common mistakes and what are the possible gaps in our revision. Now, question 1 here is a classic example of your reading of micrometer screw gauge. Okay, now micrometer screw gauge, the reading, okay, is I would say the common thing that we always like students to remember is that remember the marking at the top is actually in ones. So it's 15, 16, 17, 18, 19, 20. Then the value at the bottom is in terms of 0.5. Okay, so how we read is we'll be looking at, especially that this is 15. So it will be 15.5 at the bottom, on top will be 16, 16.5, 17, 17.5, 18.5, 19.5, 18.5, 19.5, then after that followed by 19.5, and then followed by 20. So the top line will be in terms of ones, the bottom line will be in terms of 0.5. Okay, so this is the thing that we want students to always remember, okay, to take note of which line is the ones, which one is the 0.5. Okay, then after that, same thing. Okay, so if you look at the value here in the picture, the value that is represented in the main scale would be 20.5. Okay, then after that, the line that is in the line, the marking in the micro scale that is in line with the datum line, which is this line. Okay, this is the number 42 line. So it will be 0.42. Okay, so the final answer, if you add it up together, it will be 20.92 mm. Okay, which is answer C. Okay, the using of the reading of micrometer screw gauge and vernier caliper is one of the instruments that require like certain technique. So if you have done your revision, okay, you should be able to do this quite easily. Like you should get the answer out within, like, I would say 10 to 15 seconds. Okay, so but if you have forgotten, you have not done your revision, or you have not completed a revision, okay, you can take a look at my chapter 1 video on micrometer screw gauge and vernier calipers, especially on the range of these two instruments. Okay, I'll leave the description link at the top right hand corner of the video. You can do and take a look, okay, for how to use and how to read the micrometer screw gauge and the vernier caliper. Now, for the second one, digital stopwatch, same thing. Digital stopwatch, I would say the reading is quite simple in the sense that because nowadays we use digital stopwatch everywhere we go. Example, it's available on the phone, in the handphone, in our smartphone, all these things. So the reading, I would not say is quite difficult. Okay, so take a look at the reading here. So the first reading here, this is 1 minute, then followed by 35 minutes and 35.26 seconds. So you will just read as what you see. Okay, so it will be question 2B. Okay, based on the reading. Now for question three on pendulum. Okay, now before we look at pendulum, one thing I always like to tell students to actually recall or to remember is that what factors affects the period of the pendulum. The period of the pendulum is primarily affected by who? By two factors. One will be the gravitational field strength of the planet, followed by the length of the pendulum. Okay, which here is the string now. Now the relationship, students, you have to take note of how are they related. The two factors that related to them, that will affect the period will be the length. For example, if I increase the length of the pendulum, okay, if I use a longer string, the period of that pendulum will actually be longer, will actually increase. So it will take a longer time if you're looking at a longer pendulum. Similarly, if I'm going to swing the pendulum in a planet of a lower gravitational field strength as compared to Earth. So let's say I go to Moon, whereby the gravitational field strength is actually much lower, it has actually decreased. If a lower gravitational field strength, the pendulum, okay, will actually take a longer time to oscillate. Okay, you'll take a longer time to oscillate. Okay, and as a result, okay, the period of the pendulum will actually increase. So in general, right, these are the two factors that will actually affect the pendulum. Okay, so students, you have to let's take note that in an ideal situation whereby if I'm going to swing the pendulum, okay, swing the pendulum, the period of each swing, the timing for each swing will actually be affected by these two factors. Okay, the gravitational field strength of the planet followed by the length of the pendulum. Okay, the relationship is like what I mentioned. The length and the period is actually direct proportion. As you know, that it's linearly related as compared to gravitational field strength. Okay, it will be up down situation whereby the lower the gravitational field strength, the longer is the period. It will take a longer time to actually swing. Other than that, okay, the angle in the ideal situation, the angle of the swing, the size of the bob, the mass of the bob, actually it will not affect the pendulum. Okay, so if you know this, you will know that the period of pendulum can be increased by what? By which of the factor? Repeating the same experiment on Moon. Okay, here indirectly is I need the students to know the two factors affecting the period, followed by the fact that the gravitational field strength on Earth is actually much stronger than the gravitational field strength on Moon. Okay, so take note of the choices that you are going to make and take note of the factors that affecting the period of the swing of a swinging pendulum. Now, conversion wise, question 4 is a conversion question, 72 km per hour. Here, what I always encourage students to do is there isn't a you don't need to remember the ratio to conversion for meter to second to meter per km per hour. Normally, what I tell students is you try to convert the units one at a time. For example, we are looking at 72 km per hour. So I'm looking at 72 km per hour. It can be rewritten as 72 km per hour means in 1 hour. So indirectly, I want to convert km to meter. I want to convert hour to second. So what I do is I do it factor by factor. So I look at the numerator first. So what I do is numerator require me to convert km to meter. Here, we all know that 72 km, 1 km is 1000 meter. So it's literally like 1 km, I multiply by 1000, I'll get it in terms of meter. So if I have 72 kilometer, I'm actually looking at 72 multiplied by 1000, you will give me the answer in meters. Okay, so then after that, what I've done is I have done the numerator. So what I look at the denominator, which is another factor. Hour to second. Okay, I will know that 1 minute is 60 seconds, 1 hour is 60 minutes. So if you combine these two, you'll know that hour to seconds, it will literally 1 hour is actually literally 3600 seconds. So actually is what we call multiply by 3600 seconds. Then after that, what you do is once you got these two factors, okay, once you can convert km to meter, hour to second, so what you do is you put them all together. Then after that, you use your calculator to do the calculations, to do the simplification. Okay, so it will be 72 times what? 72,000 divided by 3600. So you'll find that the answer that will give you, it will be C, 20 meter per second. Okay, so check your calculation. Okay, check your conversion. If you see the way I handle is that whenever I do the conversion, I always do it unit by unit, factor by factor. Convert 1 unit at each time. Where then it will be easier to know like how many zeros am I looking at, how many zeros should I have at the numerator, how many zeros should I be looking at the denominator. We convert unit by unit, factor by factor. Okay, now number 5 will be the speed time graph. Now, speed time graph here, what we're looking at, when we look at speed time graph and we look at acceleration, the relationship between these two is the fact that, okay, for gradient, is also known as, for acceleration, is also known as the gradient on the speed time graph. So indirectly, when I ask for which part of the graph has the greatest acceleration, I'm actually asking for which part of the graph has the greatest gradient. Okay. And when I say greatest gradient, it will actually means steepest line. It will be a steepest line, and its acceleration, it will mean that it's a positive straight line. Upward sloping, okay, steeper straight line. So what we do is you look at each of the line. For example, A, if you look at the gradient, the tangent is roughly here. So this will be roughly the gradient of the object, the gradient of the line at A, or what we call the speed of the object at A, of the bus at A. As for B, you'll find that if B is this point, the gradient of this B will be cuts the curve 1 time. Okay. So you'll find that the purple line will be the gradient for that point at the ground, on the graph. So you'll see that the purple line and the blue line, you'll find that the purple line has a steeper line. Steeper is a steeper. Okay, steeper gradient. Steeper gradient, it also means that, okay, it will mean it will be the greatest acceleration. Because acceleration, if you look at speed time graph, is actually looking at the gradient of the line. So if I want to find the greatest acceleration, I'm actually literally asking the student to actually look for the point whereby it has the steepest gradient or the steepest line. Okay, and true enough, B will actually be the line, will be the point on the line whereby it has the steepest gradient. As for question 6, okay, question 6, I will not dwell too much on question 6, because question 6 is a simple application of the formula. Acceleration is equal to final minus initial velocity divided by the time taken. Okay, here the thing we need to take note is that what is the initial speed, what is the final speed. Based on the question, it changes from 5 meters per second to 20 meters per second. So 5 meters here will be the initial speed. The 20 meters per second will be the final velocity. Okay, so it'll be final velocity minus initial. Okay, so take note of the formula and substitute the formula accordingly. Now for question 7, I would say is a classic example of like to identify the instruments to measure to measure the mass and weights. Okay, so take note of the thing. Okay, for electronic balance. Okay, electronic balance is what we always use to measure the mass of the object. Mass of the object, the easiest nowadays we are looking at is actually electronic balance. Okay, we actually it's the one that we always use at home, that we put the item on the pen on the plate, and after that the number will come up from to measure the mass in grams or in kg. Okay, then the weight of the object, straight away you will know weight of the object is always what we call spring balance. Okay, spring balance is to measure the weight of the object. Okay, so something that it's a rectangular box like that. Then after you attach something below, you attach the object below. Then after that, you have a spring that after you extend. After you show the reading on the panel on the balance itself. So that is what we call measuring the weight of the object. Now for mass itself, right? Other than electronic balance, the older version that we have is actually what we call your bin balance. Okay, beam balance is like those that you see, maybe you see in those Chinese traditional medicine, all these things, whereby you have maybe the guy holding on to the middle of the rod, then the object is being placed on both sides. So there will be a standard mass that's placed on both sides. On one side, then maybe the object that you want to buy will be here. Okay, so what we do is for beam balance is that once I will put the necessary weight, then the mass on here. So once the beam is balanced, I will know how heavy the object, the unknown object is going to be. So that's what we mean by beam balance. It's usually used like many years ago. You say nowadays everybody is like more electronic, more digital stuff really. So beam balance is actually not really used, but it's definitely one of the instruments that we actually use to measure mass of the object. Now, for question 8, the mass, the volume, the density of the thing, okay, density of the object. Now, density of object here, we look at the liquid density, 1.1 gram per cm cube. Here, what we are looking at is we want to test the students' understanding of floating and sinking. Now, floating, like we all learned in your primary school, for you to float, okay, for floating, okay, you are looking at the density. Okay, your density has to be lighter than the object itself. Okay, what we call lighter or equal than the liquid itself. Okay, so your density has to be the same, minimally the same or lighter or smaller so that you can float. For sinking, definitely sinking, okay, the density of the object, okay, it must be bigger or higher than the liquid itself. Okay, even like a 1 gram per cm cube higher, the object definitely will sink already. So what we do now is once you know this understanding, okay, so what we do now is we will actually move on to calculate the density of the object. Here, take note of the formula. The density, the formula that we are looking for, the density. Okay, the formula that we are looking out for is, remember, is mass over volume, not the other way around. Mass divided by volume. So here will be 50 divided by 20, 20 divided by 20. Okay, so here you will know, if you look at a calculator, you will know that actually G, okay, the density of this liquid G is actually 1 gram per cm cube, which is definitely, okay, lighter than the liquid. So definitely G will actually float. So G will definitely float. Okay, then after that, you look at A 50 divided by 20 is confirmed more than 1.11, slightly more than 1.1. So confirm F will actually sink. Okay, so F will definitely sink because it's more than 1.1. Okay, so F will actually sink. G will definitely float. F sink. Then after that, you have G floats. Okay, so the only one that fits this condition is actually option A. So that's why I will know that option based on the density. Okay, G will actually float, F will actually sink. Now, question 9 is on your buoyancy, on your moment, okay, or stability. Now, why does the boat become unstable when the man is trying to stand up? Now, when you look at unstable in general, we have two factors that affect stability, which is the position of the CG and the base area. Okay, and now since the boat is remaining the same, okay, so the base area that we are looking at for the object is actually the same. Okay, the boat still remains as the boat, nothing has changed. So what happens is when I stand up and sit down, okay, what happens is when I sit down, the CG I would say is roughly at this corner here. But when I stand up, because now when I stand up, the mass or the weight, the mass of the object, actually the mass of the system, the man and the boat actually is slightly increased in height. So literally like the CG will actually increase, okay, to counteract or to balance up the weights distribution. So what happens is when the man is trying to stand up, what we actually see is actually the CG of the object actually become higher. CG object is higher now. Okay, so when the CG of the object is higher now, it will mean that the system or the boat will become more unstable. Okay, it's the CG. Stability, stable or not stable, it probably depends on the CG or the location of the CG and the base area of the shape of the shapes. Okay, it has nothing to do with the weight. Okay, because in fact the weight doesn't change. If the weight increase or decrease because just because it's the person stand up, I think it's like quite an impossible task. Okay, so take note of the option here. So the option here will be A as the answer. Now, which of the following convert gravitational potential energy to kinetic energy? Okay, this one I will not do too much. Okay, most of the students actually got the correct answer for this particular question. Now, a slice of bread toasted on electric grill, which is the grill is here on top, the bread is here. Okay, which are the form of energy transfer from the grill to the bread? So it's from the grill to the bread. So it's from this area here. How does the grill convert the heat to the grill itself? Now, take note of the placement of the grill. Okay, the placement of the grill is on top, the bread is below. So we are looking at, if you heat up the object, if you heat up the grill, you'll find that there will be hot air. Hot air will actually be present because it's the grill is getting hot. So the air around the grill will actually be hot. The air around the grill will actually be hot, okay, because the grill is activated. So when you look at hot air, okay, hot air being less dense, it actually will rise. So my hot air will actually go higher. So you will not come in contact with the heat, with the bread at the bottom of the grill, because if you look at convection current, the air you're looking at, which is hot air, will actually rise, okay, because it's less dense. So which means it will not be convection. Okay, same thing because of the placement of the grill. Okay, heat, when it's hotter than environment, radiation will actually take place. Okay, the heat will be radiated out from the heater in all directions. Okay, in all directions. And likewise, part of the heat that's radiated out will actually heat the bread, actually will toast the bread. So definitely, if you look at radiation, it's definitely one of the answer. Okay, so now the only option is, okay, what is between A and D? Is D the only option? Where is D is the answer whereby radiation is the main method? Okay, or are there other methods that we are looking at? So here we must be careful. So if you look at the system, you'll find that the bread, okay, is in between the grill is above the bread. There is a layer of air here. There's a layer of air. Okay, so which means the top layer of the air will actually be heated up. So same thing, air, okay, is a medium, and it's actually, when air is being heated up, the air molecule will actually vibrate very fast. And as a result, they will collide with each other. And when they collide, you'll find that this thermal energy actually get transferred from the molecule to the neighboring molecule. And as a result, the heat is actually being transferred. So what we are looking at is actually conduction taking place, but conduction is taking place from the top of the layer, from the top of the grill, from the bottom of the grill or the top of the bread. The heat is actually being converted down, okay, to the bread itself. Okay, so it's being converted down, okay, layer by layer until it hit the bread. So effectively, I can say that the heat is actually radiated down towards the bread, and heat is also being conducted to the bread itself. So that's why the option will be A, which is better, is a more accurate answer as compared to your option D. But of course, if D will be correct, if I say I want the main mode of heat transfer, the main mode is actually radiation, but it is not the only mode. Okay, there's radiation and there is actually conduction here present in the system. Now, question 12, evaporation. Okay, evaporation, the moment you talk about evaporation, there are a few things that we always tell students to take note of it. Evaporation occur where? It occur at the surface. Then after that, evaporations will cause when the faster molecule actually left the surface, okay, of the liquid. It actually caused the liquid to actually drop in temperature, okay, because the remaining particles are the slightly less energetic particles, and because of that, the temperature will actually be decreasing, or actually be decreased. Okay, so these are the few things that you need to take note when you look at evaporation. Okay, it occurs at the surface of the liquid, and at the surface of the liquid, when the most active particle actually left the system, the remaining liquid actually consists of particles with having a lower kinetic energy. And because it's a lower kinetic energy, the temperature of the object is actually decreased. So this is what sometimes we call when evaporation occurs, you have what we know as a cooling effect. Okay, so now what happened is energy escape. Okay, so describe how evaporation works. Okay, so now what happened is at the surface of the liquid, the high energy molecule actually left the surface. Okay, so this is what actually happened at the surface. The high energy molecule actually leave the surfaces. So with the first statement, you actually can eliminate C and D already. Okay, because C and D talk about low energy, which is wrong. Okay, you are high energy at at the top. Okay, you escape. Okay, so now what happens is when the higher energetic particles actually left the surface. What happened is the liquid, okay, the remaining liquid that's left behind, the kinetic energy will actually be lower, or aka the thermal energy. Okay, the object will actually become cooler. Okay, or what we call the object actually loses the thermal energy, so it become colder. Okay, it become cooler. Okay, then what happens is we will say that when evaporation occur, okay, it actually has a cooling effect. Okay, that's happening to evaporation. Okay, which of the following way is not an application of ultraviolet? Okay, here remember for EM magnetic spectrum. Okay, you must remember. Okay, the arrangement of the particle. What's the waves? What are the waves available? Where in terms of your wavelength and the frequency. For example, if I want to know how to arrange the EM spectrum waves, the component of the EM spectrum wave in increasing order of wavelength, or maybe decreasing order of frequency. So I must know which wave occur first, which wave belong to the first section, second section, third section, all these things. Okay, so take note of the impact of this question. Then after that, what we have is other than knowing the wavelength and the frequency of the EM waves, we also want to know the users, okay, of these waves in different industry. So you need roughly know a few of what happens to the usage. For example, infrared is for remote control. Okay, your ultraviolet wave is raised for forgery detection. Okay, forgery of notes. Okay, so you must know what is happening. Okay, now application of ultraviolet. Okay, ultraviolet. Okay, what's the purpose? Okay, detect fluorescence in currency. Okay, then confirm. Then after that, kill cancer cell. Okay, no, definitely not ultraviolet. Okay, ultraviolet wave. Okay, the frequency that we're looking out for, or the energy we're looking out for, is actually slightly lower. So you is actually considered weak. Okay, too weak to kill any cancerous cell. Okay, so this one most popular answer is B already. Ultraviolet ray is definitely used to kill sterilized swimming equipment. Okay, then after that, same thing is actually used for sun tanning. Okay, so among all these options, okay, B is the one that actually looks more reasonable, accurate in answering the question. Then same thing question, 14 is the standard range that we look at, audible range. It ranges from 20 hertz to 20 kilohertz. Okay, so you must know the conversion. So we are looking at it ranges from 20 to 20 kilohertz. Okay, so this is what we mean by your audible range. So within the range, okay, 22 kilohertz is out of the range. This one is 2.2 million hertz, no out of the range. 2 hertz is out, so only left with B, which is more than 20 hertz. So remember, it's 20 hertz. Okay, more than 20 hertz is actually audible range already. Okay, so know the range. Frequency, okay. Sound wave, like I mentioned before, for this particular topic, sound wave, okay, when we are looking at the waveforms, okay, we are looking at two things. We are looking at the amplitude of the waves, followed by the frequency. Amplitude of the waves, okay. Amplitude of the wave, it means from the equilibrium position all the way up to the crest. There is your trough. This is your amplitude, sorry. Okay, now this amplitude here, same thing, is always measured from the center to the highest point, crest, which is the amplitude. Or it could be measured from where? Down to the section here. So this will be the amplitude. Okay, it's always measured from the middle line all the way up to the crest, or all the way down to the trough. After that, we will look at frequency and amplitude. What does it control? Amplitude control the loudness of the sound itself. The higher the amplitude, the louder is the noise. Frequency, okay, it controls what we call the pitch. Okay, so if you are looking at the frequency, so if you are looking at frequency, okay, of one cycle, okay, the frequency, or what we call the period of one cycle, you'll find this is the period. Okay, and then how does it relate to frequency? It's because for frequency, we do know that your period and your frequency, they have an inverse relationship. So which means that the higher the period, the shorter is the frequency. Okay, so when I want to describe R and S, when I want to describe waveform, usually I look at two things, your amplitude and your frequency. Okay, so indirectly what we are looking at is this. Okay, so if I look at P and Q, they are definitely the same loudness because P and Q has the same amplitude. Okay, so PQ confirms softer than RS. Okay, so softer wise, PQ, SR. So PQ, they should be the same. It's out. Then QR is louder than R. Q is louder than R, definitely. R, no, wrong. Q is not louder than R. Q is not louder. Why? Because amplitude. Okay. Sorry. Louder, yes, louder. Okay, so Q will definitely, the amplitude of the wave is actually shorter than the amplitude of R. Okay, so if you look at the placement of the wave itself, you'll find that actually Q is actually softer than R. Okay, so that's why B is out. Okay, then after that, okay, we look at R has a lower pitch than S. R has a lower pitch than S, it means frequency of R is actually lower than frequency of pitch. Okay, so take note of the wave itself. So you'll find that if I look at the pitch, okay, R definitely will have a lower pitch because the period of the wave is actually quite big as compared to S. Okay, S, the frequency, the time for one cycle is actually smaller. The time for one cycle is actually smaller. Okay, and because the frequency, the period is actually now the period is actually shorter, you'll find that S is actually having a higher frequency. So which means S will be a higher pitch as compared to R. Okay, always take note. Okay, the relationship for frequency is a slightly tricky one. We look at the frequency, the pitch of the sound, we draw references to the wave, and we also draw references to the wave itself. Okay, so take note of the wave, okay, especially the pitch and the loudness. Now, as for question 16 will be a circuit question, okay, whereby the light bulb is up and down, two light bulb, one light bulb up and down, then followed by a battery, the cell and the batteries in the middle. Now, if you look at the question you are looking at, the question is asking for convention current and the electron current. Now, take note of convention current. Conventional current that we are looking at is always from where? It's from the positive terminal of the battery to the negative terminal of the battery. Okay, so in terms of drawing, okay, the positive terminal is actually what we call the long line. The long line. Okay. The negative terminal in terms of drawing, it will be actually the shorter line. Okay, so in the sense that this long line here will be the positive terminal. This short end here will actually be the negative terminal, which what we always know already. So here what we need to take note is that in terms of the positive terminal, convention current is always from the positive terminal to the negative terminal. For electron current, okay, so if you look at conventional current from positive to negative, so the positive terminal, so the current will actually be coming out from this corner, okay, moving to the right. So when it hits the nodes, the junction, one will go up, the current will split up, the another current will go down. Okay, so for lamp S, the current will be going from right to left, going up again. As for lamp R, you'll find that the current is going from right to left also. Okay, then after that go down. So when they meet up at the node again, they will combine and they'll go back to the battery again, the negative terminal of the battery again. So the blue color line would be the conventional current. So for lamp R for conventional current is actually going from right to left. Okay, so R is right to left. So R is right to left, right to left. Okay, so now if you look at electron current, now electron current will be the reverse. So if you look at electron current, look at how the electrons actually flow, okay, from the battery. So it's always from where? It's always from the negative terminal to the positive terminal. Okay, so for electrons, it will be going from the negative to the positive. So negative terminal is here. So if you go negative terminal, okay, you from negative terminal, okay, out. Then after that, hit the junction, hit the node. One of them will go up, the other one will go down. Okay, so what happens is on the lamp R, the current will be going from left to right. Okay, then go back again. For lamp S, you also be left to right. Then after that, combine back to the next node and go back to the battery again. So for the electron current is actually from negative terminal to the positive terminal. So if you look at the paper, if you look at the junction here, okay, if you look at the picture here, you will find that for lamp S, okay, the electron current from lamp S will be from left to right. It will be this particular direction. So the combination of B and two direction will give you that C will be the correct answer. Okay, so conventional current, take note, okay, conventional current is from positive terminal to negative terminal. Electron current will be the reverse. It will be from negative terminal to the positive terminal. Okay, because electron current, look at how the electrons in the wire actually flow. Okay, so take note of the two current flow, the conventional current and the electron current. Now, the common question that I get is that which current should I use if I look at circuit? Okay, now for circuit, we always look at the conventional current. We always treat the current as flowing in the conventional current. We will not look at current as in the electron current. So just take note, okay, for all calculation, the current flow is always based on conventional current. Okay, and after that, same thing. Okay, you look at the formula for charges, both potential difference and resistance. Okay, for current, okay, there's this formula, charge over time per unit time. Potential difference will be the energy divided by the charge, followed by resistance will be rho L over A. These are the three individual formula for these three individual factor: current, potential difference, followed by resistance. So what is the amount of charges flowing across the resistor? Charges across the resistor, okay. So we are looking at Q. So the easiest, I would say, if I want to calculate Q, okay, what I want to do is maybe I will want to look at in terms of, let's say, current. So if I want to look at current is Q over T. Okay, the amount of charges that I'm looking at. So if I rearrange the formula, it will be Q equal to IT. Okay, current. Okay, now, so same thing, time taken, time is actually 4 seconds. So I have the time ready. I got the time. So now what I'm looking out for is actually I got time. So now what I lack now is actually the current. Okay, so what happens is I should go and look at the current. So then current, okay, remember, other than the three basic formula, we have one main formula that we always like to use, which link all the three factors together, which is Ohm's law, V equal to IR. Okay, so you know the resistance is 3 ohm, and you know that the potential difference is 12 volts. Okay, so you use V equal to IR, you'll be able to calculate the current is actually 4 amp, 12 divided by 3. So once you have the current, okay, which is 4 amp, what you do is you substitute back into the equation. Okay, so it will be a standard, what we call 4, which is the current, multiplied by the time taken, which is 4. 4 times 4, it will give you a 16. So we have 16 coulomb. Okay, so this is the formula that using the formula you should be able to derive the answer for the charges is 16 coulomb. Okay, here what we are looking at, for you look at is, even though it's a simple calculation, but we are looking at not just a one-step approach calculation. Okay, here you are looking at 2 steps approach, whereby actually the marker will actually need the students to actually do a first layer of calculation. Okay, using the formula Q equal IT to actually identify what are the missing factor, which is current. Then after that, we look at the second layer of calculation. Is that because I know I need current, so I will look at what are the formulas that allow me to calculate current. And the formula that allows me to calculate current is the Ohm's law, V equal to IR, because I have all the components. Okay, so this is what we mean by a two-step calculation. Okay, MCQ doesn't mean, well, I do one step, one working, the answer must be out already. No, it doesn't work that way. Right? Some question, yes, it's a simple one, yes. But some question which is like slightly complicated, you'll find that you may actually need like to use maybe 2 or 3 formulas before you can actually arrive at the answer. Question 18. Question 18 is a classic example of using the resistance, which I mentioned earlier. Okay. Now the resistance formula, which I mentioned earlier, rho L over A, which is here. Okay, this formula. So which of the resistance has the highest resistance? Okay, so if I want the resistance, if I want R to be the biggest, you'll find that my length has to be the biggest. My denominator, which is the cross-sectional area, has to be the smallest. Okay, so for my wire to have the greatest resistance means I want L to be big. So it definitely 100 and 200, so definitely 200 has to be big. If I want the area to be small, so which the diameter of the cable must be small, so it be 0.01. Okay, so the factor that the option that has all these components will be actually option C, whereby I look at long length and thin wire, okay, which is a smaller cross-sectional area. And these two numbers will result in what we call the greatest resistance value. Okay, so this is what we mean by you need to know the basic formula before you can actually start to do the question. Okay, question 19. Okay, which of the following is concerned of exchanging the live and the neutral cable? Live and neutral cable, remember, okay, live and neutral cable, the important thing about live cable, why do you want to specify live cable is because I can put my fuse at the live cable, I can put my switch at the live cable. Okay, this is the purpose, one of the main purpose of the live cable, to indicate where should I place the safety precaution. Okay, but other than that, the live and neutral are just two different wires. Okay, you can just swap them around. Okay, current will still work one. Okay, so the appliances will still work. So nothing, it will not blow one. The appliances will not spoil. Okay, it will not be suddenly consuming more power. Okay, so what happened is the appliance will still function as per normal, like what I mentioned. Okay, but what happened is now your fuse and your switch will not be active already. Okay, because why? Because the object is actually connected to the high potential, which is always connected to the positive terminal. Okay, so even though the potential, the item could be switched off. Okay, why? It's because the switches and the switch and the fuse are at the wrong location. Okay, now which of the following will occur? Okay, if you look at the question, it's more like maybe you're looking at fuses and the practical electricity. So now what we do is I have a 30 amp fuse fitted inside. So what we do is if I look at 30 amp fuse, I must look at the current that is in the iron. So the current, if I use V equal IR, okay, you'll find that current is actually V over R. Wrong formula. Okay, if I use the formula power equal to IV, okay, power is 2,400. Current is what I need to find plus 230. Okay, so you'll find that actually, if you look at the question here, let's say, let me do a calculation. Okay, so your answer, your current, if you use a calculator, will be 4.3 amp. Okay, if you use a 30 amp, okay, if you use a 30 amp, okay, the current, the ampere, the fuse rating is 30 amp, your working current is 4.3. So you'll find that your working current is still lower than the fuse. So which means when 4.3 amp of current actually flow through the cable, okay, and flow through the fuse, okay, you'll find that the fuse will not melt one because the current, the working current is actually still lower than the fuse rating. So what we do is the iron will actually operate as per normal. Nothing changed really. Okay. Here, take note is we use different formula like power equal IB. After I look at the possible value for the fuse. Okay, so these are like what we mean by a common approach towards using power and including safety precaution. Okay, so with this, we will come to the end of your chapter paper 1. Okay, paper one, I would say is not difficult. It's just that maybe for this question, it's a bit time consuming. So students will need to actually do a bit faster so that you can have enough time for paper two. Okay. Okay, for question one, right? Question one here, what we are looking at is a dynamics is on Newton's law. Okay, whereby a luggage is being pulled by a force F. Now, things to take note, like I always tell students, that the use of the word constant speed. Constant speed, okay, take note, don't mix up with constant acceleration. Okay, here is constant speed. Constant speed, the clue that they are telling you, right, is that the object is moving at constant speed, which means the acceleration of the object is actually 0 meter per second square. Okay, so the clue that behind the using of this statement, constant speed, actually tells students that the acceleration is actually 0. Okay, and because the acceleration is 0, you'll find that when we apply Newton's law, okay, F equal ma, F net equal ma, the right side of the equation is actually a 0. Okay, because acceleration is 0. So the net force applying on the object, okay, there is one force that's applied, and based on the question, there is a second force in the question, which is the friction. Friction is acting on the wheel, which is between the wheel. So this is where the friction is. Okay, look at where I draw the friction. Okay, the location of the friction has to be important. Based on the question, it's between the wheel. So it has to be drawn at the correct location. Okay, so you have two forces. One is to the right, one is to the left. If you take the net force, it will be the applied force minus the friction, F minus F. You rearrange the algebra, you'll find that the frictional force actually will be 45 Newton. Okay, so the frictional force after calculation, it will be 45 Newton. Okay, then after that, what happened in part B? Part B, the question will say, oh, the applied force actually increased from 45 Newton, now it increased to 80 Newton. Now, then after that, they make another variable, okay, whereby they change another variable is to say that instead of moving at constant speed, now it's moving at constant acceleration. So when you look at constant acceleration, right, here there is an acceleration, okay, which is a number, okay, which means that if you look at Newton's second law, F net equal ma, okay, if you compare to question A, okay, question A, F net equal ma, the right side is 0. Okay, but now if you look at part B, F equal ma, because now acceleration is a number, you'll find the right side, okay, is actually a number, which is not 0, take note. Okay, so which means you are supposed to, based on the question, you're supposed to find the acceleration of the object. Okay, so of the luggage. So what happened now is, when I increase the force to 80 Newton, okay, and there is an acceleration. So if you do the same thing, you look at Newton's second law, you apply net force. You'll find that now is applied force minus the friction. Okay, so you'll find that applied force is 80. Okay, right side is not 0, it's 28A. 28 is the 28 kg. A is the acceleration. Things to take note is that when you apply Newton's second law now, okay, other than the fact that right side acceleration is a number, the friction force on the object is actually remains the same, because the friction force on the object here we are looking at is on the same floor, the same wheel, the contact area is the same. So the friction that we are looking at is actually remains the same number, which is 45 Newton. So the friction here, 45 Newton, is because the floor and the contact area, the item is actually remaining the same. So the friction will remain the same. Okay, so the net force now will be actually a 35 Newton on the left-hand side. Okay, 2 and 8A. If you rearrange the algebra, you'll find that the acceleration will be 1.25 meter per second square. Okay, so if you look at part A and part B, you'll find that these two examples, this pattern of asking, okay, it's quite a standard way, a standard application of Newton's law, whereby the question starts off with 0 acceleration, or what we call constant speed. Okay, and usually they will ask you to calculate the friction or applied, or maybe the resistivity force. Then after that, part B, the question will say that something happened to the force. Okay, and after that, they will ask you to calculate the accelerations. Okay, so I would say part A, it looks a bit demanding, but actually the approach, the solving technique, the thinking process for part one, question one, is actually quite a standard. It will fall under the easy section. Okay, so I would say question one actually, okay, despite the look of the use of the math or this, question one is actually quite easy. It's what we call a safety net question. Question two is, I would say it's another easy question. Okay, the only thing that you have to be careful is the usage of the formula. Okay, density of the box X. Okay, density formula is mass over volume. Take note, don't miss the formula. Okay, some of you like to use what volume divided by mass. Okay, mass times volume. Okay, use the correct formula. Okay, then after that, based on object X, okay, calculate the volume, calculate the density. I will not say this is difficult. Okay. Then after that, block Y is rotated and placed on the table in various positions. So for example, block Y could be facing downwards horizontally, or block Y could be in this orientation. Okay, so this is what we mean by different orientation. Okay, different orientation of box Y. So they are looking for maximum pressure. Okay, now maximum pressure, same thing as part A, use the correct formula. Okay, pressure is denoted by the formula force divided by area. So if I want pressure to be maximum, okay, since the box, I can't change the box, the mass of the box, the weight of the box. So if I want maximum pressure, it will mean that the area, the denominator has to be minimum. The area has to be smallest. Okay, so which means being the smallest area, okay, being the denominator being the smallest, it will make the pressure to be at the highest, the maximum. So to have a minimum, what I call area, it will mean that box Y has to be seated on the table, okay, with the area 2 by 2, okay, in contact. So it will look something like this, okay. Oopsie, sorry. Okay, so the contact area could be 2 by 2. Okay, this is the contact area, which is facing the floor now. Okay, so this is box Y. Okay, so when we talk about different orientation, it's literally you have to actually take the box and actually rotate it at different orientation. Okay, whether it's sitting down, standing up, all these things at different orientation. Then you can calculate the maximum pressure. Okay, so question 3. Okay, oh yeah, talking about question 2 here. Okay, when the question asks for maximum pressure, another twist for this style of question is that instead of asking for maximum area, maximum pressure, I could be actually asking for minimum pressure. Okay, minimum pressure, whereby the object will be, in this case, will be lying on the contact area with the biggest contact area. Okay, so the orientation of the blocks actually makes a difference in terms of the pressure exerted on the table. Now, for question 3, question 3 will refer to, I would say the question will be mainly based on like transfer of thermal energy, which is like your conduction, convection, radiation. Okay, so here it's important to identify the mode of transfer based on the clues that's given. Okay, now we question here, outer surface of the pot is black matter. Okay, so when you look at black matter, there are two things that the question is trying to tell you. Okay, so when you talk about, first thing we talk about matter, it refers to the material of the object. Okay, it refers to the material, and whenever we deal with material, the mode of transfer that we're looking at is primarily on conduction, whether it's conduction fast, slow, all these things. But regardless of whether fast or slow, when we talk about matter, we talk about material, the clues given to us, which is matter, which actually belongs to the material section, it actually tells us the mode of the transfer will most likely be conduction, about conduction. The other perspective about the other clue that's given to us is actually the word black. Black here refer to the color. And when we deal with color, okay, the clue that's pertaining to color, okay, the mode of transfer that we are looking at is actually what we know as your radiation. Remember, radiation actually involves, okay, several clues like the area, the size of the context of the item, okay, the texture of the item, okay, the color of the item, followed by the temperature of the item. Okay, so these four are actually what we call the basic clues for radiations, to hint to people, to hint to the readers that actually the questions wants to highlight the process of using radiations. As for conduction, like I mentioned in the channel on transfer of thermal energy, okay, if you look at convection, is usually referring to the location, you know, whether the object is up, down, whether the hot air or hot liquid can be flowing up and down, all these things. Okay, so for the clues of transfer of thermal energy, I mentioned again, okay, the clues of transfer of thermal energy is, I have actually listed out in detail in my video for chapter transfer of thermal energy. I think it's chapter 8. Okay, I'll leave the link for that, for the clues, okay, in the description bar below. So if you want, you can actually click on it. Okay, if not, I also place the link on the top right corner of your video. Okay, so if you want to get a revise on it, or want to get a new look, a fresh look on it, you can click on the video, okay, and to look at what are the clues available for conduct, convect, and radiations. So when you look at black, okay, so that's why in your answer, I will actually know how to explain I will know how to write, I will know what's the answer for the question. So when the question say black matter, I'm looking at answer, not just to explain black, not just to explain conduction, it's actually I need to explain both of them. So that's why 1 mark is given for when mention of black. Explain why black is used, because black, like we mentioned, is a good absorber. He absorbs heat by radiation. And I also need to explain why the use of metal, because metal is a good conductor. Okay, heat conductor will actually be faster. Okay, heat gain will be actually higher. So that's why I know that actually the 2 marks here consists of actually 2 methods. Okay, conduct and what we call radiation. Okay, it's not about like 1 mark is about conduction. Then another 1 mark is about explaining conduction. Okay, so in this case, it's not about elaborating more details for 1 method. It's more like the question is asking for 2 methods. Then after that, the question talk about heating curve of substance X. Okay. Then after that, substance X melting point. Okay. The clue about this is melting point. So when you have 2-step process, this section, the first horizontal line you're looking at for heating phase, the first horizontal line will be what we call the heating phase. Will be what we call the melting phase. Okay, then after the second horizontal line that you see, it belongs to the boiling phase. Okay, so in between, if you know the heating and boiling stage, you will know that the first section A, B here will refer to the heating process. The second here will be the heating process. And of course, the second heating line that you see is actually heating of liquid. The first heating line that you see is actually heating of solids. Okay, so melting point of X, okay, is actually this line here, which is 40 degrees. Okay, so know how to read the heating curve. Okay, and after that, same thing, like I mentioned I think in the previous paper. Okay, when we talk about internal energy, when we talk about heating curve, we are dealing with internal energy. Internal energy we are dealing with is we are looking at the kinetic energy, and we are looking at the potential energy, okay, of the molecules. Okay, kinetic energy, like okay, the details or the keywords for kinetic energy. For example, kinetic energy, when we talk about kinetic energy, we usually look at the temperature of the molecules or the substances. Potential energy will refer to the intermolecular bonds weakening, followed by the change of state. Okay, so the detailed keywords, what to write, what are the keywords? Okay, I mentioned it in that topic. I think it's chapter 9. Okay, transfer of thermal property. Okay, I'll leave the description, the keywords in the video here. Okay, for you to take a look. What are the keywords to write? Because at each stage, okay, A, B, what I call stage 1, B, C, stage 2, C, D, stage 3, and subsequently D will be stage 4. At each stage, I need to write the exact behavior, exact keywords pertaining to that stage. For example, at stage 1, I will need to talk about kinetic energy, okay, making reference that the potential energy actually remain constant. So at each stage, there are tagging keywords, there are relevant keywords that has to appear to illustrate your understanding for that particular process. Okay, so take note of the keywords. In addition, okay, we also need to look at the kinetic model, or what we call the property of each of the stages. Okay, when I'm talking about liquid, what happened to the liquid? What happened to the property in terms of what? In terms of the arrangement. Okay, in terms of the arrangement. In terms of the arrangement. In terms of the motion. Okay, and in terms of the intermolecular force. For example, if I'm looking at the liquid, okay, if I'm looking at liquid CD, if you look at liquid, if you look at the arrangements, you'll be looking at the particle is moving. Okay, you'll be able to move. Okay, they are close to each other, but they are able to move. They are able to slide against each other, across each other, over one another. So in terms of arrangement, if you compare to solid and liquid, okay, solid has the arrangement to say that they are bounded fixed in their position. They can't move, okay, except vibrating at their fixed position. But for liquid, okay, out there they are still relatively they are still fixed at their position, but the intermolecular bond is actually weaker, and because of that, they are able to slide across each other. They are not bounded in place like solid state. In terms of intermolecular forces for liquid, okay, it's slightly weaker only. It's just a bit slightly weaker only. Okay. So if you look at solid being the strongest, okay, liquid will be the second tier, will be less, will be under the strong intermolecular bonds. Okay, so the forces, the property of solid states, the molecule in solid state, liquid state, and gaseous state, okay, they have their own individual behavior in terms of where? In terms of their intermolecular force, in terms of their arrangements, and in terms of their motion. Okay, so these properties, these factors actually will dictate the property of the substances at each stage. Displacement time graph. Okay, for displacement time graph, the first thing we look at is displacement time graph is to look at the amplitude. Okay, the sound graph or wave graphs is always looking at the, we always have the same approach. Whenever I given a wave graph, I will actually look at amplitude first. I'll identify where is the amplitude. So this is the amplitude from the zero, the equilibrium position, to the crest or to the trough. Okay, so this will be amplitude. Then after that, I'll identify where is the period, where is this one cycle. So one cycle, if this is a cycle, this will be the one cycle. So the one cycle on the x-axis will be ranging from here to here. And because the x-axis is time, so one cycle, and in this graph, x-axis is time, one cycle here will actually refer to a period. Time taken for one cycle. Okay, so from this graph, I actually know that the amplitude is 0.2. Okay, and I know the period is 0.02 seconds. Okay, and based on the question, the wavelength is 0.5 meter. Okay, so based on the information I have, is you take a look. I have the period which is 0.02 meter. I have the amplitude which is 0.2 meter. Okay, so this is the information that is given to us, and also wavelength is 0.5 meter. Okay, so these are the three information that is given from the graph. And simple enough, they are asking for the frequency of the wave. Okay, so the formula we have to always remember is F equal 1 over T. I will not say this is, I will not think this is difficult. Most of us will know the formula. So you know the period is 0.02, oh no, meter is 0.02 seconds. Okay, so you put your calculator, you'll find that the frequency of the wave is actually 50 hertz. Speed of the wave will be V F lambda, the wave formula. You get answer 25 meters per second. Okay, quite easily done. Okay, not much difficulty here. Now, section B here is whereby the students are required to actually choose 2 questions out of 3. Yeah. So remember in your paper on the day of the exam, okay, remember to read the 3 questions first. Okay, don't just do question 1, the first question, okay, on section B, just because first question could be the easy, or don't just do question last question because you thinking that the last question could be easy. Okay, remember, spend at least 1 minute or 2 minutes, okay, of that time, of your time. Okay, read through all the questions, all the 3 questions in section B first. Then after that, choose the most suitable 2 questions. Okay, the suitable here in the case that, of course, if you look at it in terms of exam, suitable here would be the questions that you have confidence in scoring the highest marks. Okay, because section B is actually looking at 3 questions, choose 2. These 2 questions were actually choosing the correct 2 questions will actually value at your marks. Okay, your marks, pushing your marks at least 1 grade higher. Okay, so it's important to choose the 2 questions that will allow you to score the most marks. That's the most important. And to do that, the first thing you must do is actually to read all the 3 questions. Now, for question 2, first question, question 5, okay, it's a bit of kinematics. You'll find that it'll require you to plot all the points, then after that, draw the best fit line. If you plot the point carefully, you'll find, and draw the line, you'll find that you will have a nice red line here, like we shown. Okay, so you get the 2 marks straight away. Okay. Then after that, we look at velocity time graph, okay, distance time graph, velocity time graph. These are the graphs that they will come out under kinematics. Okay, so for displacement time graph, distance time graph, we are looking at distance time graph. Okay, so we are looking at the gradient of distance time graph. Why gradient? Because the gradient will actually give us the speeds of the object. Okay, that's the important thing that we will tell, that's important from this graph. And of course, if you look at the graph itself, it will actually give us the distance of the object with respect to the time. Okay, so these are the information that we have. Calculate what is the distance traveled after 2 seconds, after 12 seconds, sorry. After 12 seconds, you look at it, you'll be here. The time taken, 12 seconds is here, time taken is here. So you can just read the number of the graph. I will not say it's difficult, so you get answer straight away. Now, moving at constant speed for first 40 seconds. This is what you mean. Distance time graph, when we're looking at the speed, we are looking at the gradient. So the question is actually asking you to calculate the gradient. Okay, so you can use your rise over run. Okay, so the change in your rise will be here. This will be the change in your rise. Your rise, then followed by your run, which is 40 seconds. Okay, rise over run, or what we call your change in y divided by change in x, you will get the gradient. And with gradient is also aka the speed of the object. So that's why for VT graph or distance time graph, it's actually important to really know what graph you are given. Because the graph, although graph, we always be looking at the gradient, we will look at area on the graph, but because different graph will give us different meaning. For example, if I have a distance time graph, the gradient will give us speed. If I have a velocity time graph, the gradient will give us acceleration. So the impact or the values that we can elicit from the graph actually differ from graph to graph. Okay, describe the motion of the graph at 40 to 60 seconds. Okay, same thing, displacement, distance time graph, when I describe the speed, when I describe the car, I will definitely need to describe the speed of the object. Okay, so for the car, for 40 seconds to 60 seconds, okay, at this junction here, the speed, the distance is actually 1000 meter, always flat. But I'm not interested in that also, because I'm more interested in the speed or in the speed of the object at 1000 meter, which means the gradient is actually constant. Okay, not constant, sorry. The gradient is actually 0. Okay, means that the speed will actually also be 0 meter per second. Remember, for distance time graph, like I mentioned before already, distance time graph, the gradient actually represents the speed. So if my gradient is 0, it also directly means that the speed of the object is also 0 meter per second. So true enough, okay, this is what I need you to write when we talk about description. Distance time graph, when I ask you to describe, you need to write about the speed. If it's velocity time graph, I ask you to describe, you need to talk about the acceleration. So for distance time graph, we're looking at the speed. So all I need the student to write is actually tell me that the speed at 40 to 60 seconds is actually 0 meter per second, or what we call stationary. Okay, or sometimes we say object is not moving. Okay, calculate the average speed for the first 60 seconds. Average speed is total distance. Okay, given that, like I mentioned before, total distance is 1000 meters at the beginning. Okay, or at the 60 seconds is stationary, at the end at 1000 meters. After you stay there for a few seconds. For first 60 seconds, total time is 60 seconds. Divided, you'll get 16.7, which is the average speed of the object. Okay, and that will be your question 5. Okay, if you look at the difficulty level, I would say question 5 is actually quite manageable. Okay, so I would definitely choose question 5. Okay, question 6 is about energy and weight and energy. Okay, whereby the object, the wheelbarrow is at the bottom of the belly or of the position. So there's a plank whereby the wheelbarrow later will be pushed up the plank. Now the wheelbarrow is the mass of the wheelbarrow is 88 kg with sand. Okay. Calculate the weight of the wheelbarrow filled with sand. So when we talk about wheelbarrow, the weight is mg, the formula. So make sure your mass is kg. Okay, and same thing, the weight, if you look at the placement of the weight, it will be at the CG. Okay, your weight will be actually be pointing downwards. Okay, so this will be the weight of the object. Weight of the wheelbarrow. Now, assume negligible energy loss. Calculate the work done in moving the wheelbarrow from X to Y. Okay, now from X to Y, okay, and the question says I push it up and the wheelbarrow stays here. Okay, so at the beginning, whatever energy I have to push it up, the wheelbarrow up the slope, all the energy will be converted at the top, will be converted because of my position at the top. So it will be converted to what we call gravitational potential energy. Okay, so from the beginning, at the beginning, when I push it up, okay, I will apply a force upwards or diagonally. You will be doing if I apply a force here to push the wheelbarrow up, okay, the force and the distance, it will allow me to perform work done on the object. That energy will actually be converted to potential energy, which is mgh. Okay, so that's why height is 1.2, 88 kg, gravitational field strength is 10. I will get an energy of 1056 joules. Okay, it takes 4 seconds to push the wheelbarrow up. So power is energy divided by time. Make sure the time is in seconds. So 1056 divided by 4, 264 watts. So that's the answer straight away. Quite easily done. Okay, now for part B, okay, the slightly harder one. Okay, based on the question, the wheelbarrow is being lifted up in this manner. Okay, after that, calculate the minimum force that's needed for the construction. Now, based on the question, you have to lift the wheelbarrow up. It's in the sense that the pivot is at the wheel, the front wheel, or the only wheel, I would say. So if you look at the weight, 100 Newton, okay, 100 Newton with respect to the pivot, okay, at A, 100 Newton will actually apply a anti-clockwise moment. I label this as M100. So if I'm applying an anti-clockwise moment M100, I'm also looking at the perpendicular distance. So between the perpendicular distance for 100 Newton here will be here, D100. Okay. So this will be the 40 cm will be the perpendicular distance for my force 100 Newton, producing an anti-clockwise moment. Then for my F, okay, for my F with respect to the pivot, my F, the perpendicular distance is actually ranging from the corner of F all the way to the pivot, which is 90 plus 40 cm, which makes us 130 cm. So the perpendicular distance DF, which is actually 130 cm, and the force F about the pivot A is actually creating a clockwise moment. I will label this as MF. So if you look at the moments, okay, you'll find that so far the two of them is balanced. So which means I will have my anti-clockwise moment balanced with my my clockwise moment will be balanced with the anti-clockwise moment, or what we call my M100 is balanced with MF. Okay, MF same thing is 100 Newton times 40, which is here. Okay, MF, this working. I shall continue here. Okay, this is 100 times 40. This is my MF. M100 will be F times, MF, what am I saying? Okay, let me repeat again. So, sorry. Okay. Now, my 100, okay, will be anti-clockwise moment. Okay, anti-clockwise moment, wrong color. Anti-clockwise moment, okay, equal to clockwise moment. Okay, so my clockwise moment, okay, based on the question, my clockwise moment, my anti-clockwise moment is M100. My anti-clockwise moment and my anti-clockwise moment is M100. My clockwise moment is MF. So if you look at the working, MF can be broken down into F times 130. Okay, so this is here. MF, I can break down to F times 130. My anti-clockwise moment M100, I can break down into 100 times 40. Okay, so if you look at algebra, you'll find that the applied force F can be calculated to be 30.769. If you look at 3SF, it will be 30.8 Newton. Okay, so this is what happened where if you use principle of moments. After that, the question look at if the handle of the wheelbarrow is going to make longer. Okay, Now, will the force needed to be larger, smaller, or remaining the same? Now, what happened is, if I increase the length of this handle, okay, if I increase the length of this handle, okay, if I increase the length of this handle, which means if I increase the length of this handle, it will mean that the perpendicular distance, this handle, so which means it will mean that when I increase the handle, it will mean that the perpendicular distance df will actually increase. Okay, so with a longer perpendicular distance, okay, I actually do not need a big force. I actually will need a smaller force to balance the wheelbarrow. The moment is force times perpendicular distance. Okay, to support the wheelbarrow, I need a number, okay, a constant number of moments to actually lift it up. So what happens is, if my perpendicular distance is longer, is now bigger, to ensure the same moments, okay, it will mean that I actually can apply a smaller force on the wheelbarrow, in the sense that it will actually make my carrying of the wheelbarrow, the force F, okay, to be smaller, to be easier. So I will actually have an easier time or a better time. Okay, I'll be more comfortable with lifting the wheelbarrow because the force actually is smaller. Okay, so take note of the question. Question 7 is on practical electricity. The first thing is to know the wiring of the cable, all these things. Okay, so this one I would say is a standard thing that all practical electricity, whenever you revise the topic, you have to take note of. Okay, the colors, the which is live wire, which is the neutral wire and earth wire. Okay, so take note. Okay, and I mentioned before, the color of earth wire has to be two colors, green and yellow. Not green or yellow, it's green and yellow. Okay. Then after that, we look at calculate the costing of the electrical iron. Cost of 1 unit of electricity is 0.19 cents. Now, if you look at 1 unit of electricity, it costs 19 cents. The 1 unit here we're referring to, we refer to 1 unit of energy. And the energy is actually in kilowatt hour. 1 unit of E, right, is in kilowatt hour, because it's in costing, so energy will be in kilowatt hour. So if you look at the formula, energy is E equal to PT. Okay, so when we talk about energy is PT, and your energy has to be in kilowatt hour, it will mean that the unit for power, it has to be in kilowatt, and the unit for time has to be in hour. So this is why one of the reasons why whenever we look at practical electricity, when we look at energy, we must know what units, what the energy has to be. If you look at costing, it always has to be in kilowatt hour. Okay, because the unit of one electricity unit will be in terms of kilowatt hour. So which means that the power has to be converted to kilowatt. The time used has to be in hour. So in this case, the question given is that the power is 2 kilowatt hours. So the P is 2 kilowatt. Just put the 2 here. Don't need to convert to watts. Don't put 2000. Time is used is 1.5. So if you take these two numbers, you put inside the formula, you'll know the energy used is 3 kilowatt hour, and 1 unit is 19 cents. So 3 kilowatt hour, 3 unit will be 0.5757 cents. Okay, so this is what we mean by calculating energy. In terms of energy, right, if it's not kilowatt hour, so if you not electricity, if you look at energy, you got PT. Another unit for energy we are looking at is energy is in terms of joules. If you look at joules, right, it will mean that the power has to be in watts. The time has to be in seconds. So it depends on what unit you are looking at. So in general, I would say electricity, the unit for energy is always in terms of kilowatt hour. Okay, and while the rest of the topic could be energy, the normal dynamics, the object falling down or lift up or maybe work done, energy is always in terms of joules. So that's why the different contexts, the unit of energy will actually change accordingly. Okay, then after that, based on the circuit, I have a simple circuit, okay, a 6 ohm resistor in parallel with a 2 ohm resistor. Calculate the effective resistance. Okay, so if you look at the formula, this is parallel resistance. So the formula that we'll be looking at is 1 over R parallel. It will be 1 over 6 plus 1 over 2. Okay, then after that, you will have this answer to be 1 over 6 plus 3 over 6. So it will be 1 over r parallel, it will be 4 over 6. Remember, you must flip, okay, you must flip to get r parallel, which is 6 over 4, which is 1.5 ohm. So regardless of the working, so some of us, we like to use R effective is 1 over, you like to use this formula 1 over R, okay, because why? This formula, it means that you don't need to flip. It is much like easier to write. But for me, I like to stick with the basic. I like to use the basic formula, which is 1 over R parallel is equal to 1 over R1 plus 1 over R2. This is the basic formula that's given. But if you use this method, remember, there is the final stage, you must remember, don't leave your answer as 1 over R parallel. You must remember to flip, because ultimately, I'm not looking for 1 over R parallel, I'm looking for R parallel. Okay, so this is the unit I'm referring to. Okay, then after you get my unit, my R parallel to be 1.5 unit, 1.5 ohms. Calculate the reading on the ammeter. Okay, ammeter here, it refers to the total current. So the easiest one is to use Ohm's law, V equal to IR. Okay, total current, I will need the total resistance, I will need the total voltage. The total potential difference here refer to actually is the EMF of the battery, okay, which is 3 volt here. Okay, then total resistance, your calculator is 1.5. So if you substitute the number inside, you use the algebra, you'll find that the current will be 2 amp. Okay, it's a simple circuit. Okay, so with this, okay, it comes to the end of the last question. Overall, for these 3 questions, right, which will be the easy question, which will be a difficult question? If you ask me, right, my personal opinion is that all these 3 questions, I will say that the first question, the kinematics question, and if you ask me, I prefer electricity. So the last question, question 7, this is the 2 questions I will choose. Okay, question 6, I will not say it's difficult nor easy, but just that if you look at in terms of calculation instead of working on mathematics, I would say that question 6 is slightly harder because I need to do a lot of questions. I need to do a lot to get the same marks. As for question 7, if for question 7, those who are we are well versed in electricity or we are okay with electricity, you'll find that actually it's quite a standard treatment for electricity question. So if you're comfortable with electricity, I would say that electricity, this question is actually fairly easy. So if I were the student, if I'm the student on that day, I will actually choose question 5 and question 7 as my 2 chosen questions. Okay, I will leave question 6 untouched. Okay, so with this, okay, we have come to the end of the N-level paper for Springfield. Okay, so you've done your paper. Okay, you might want to check the question to check all the keywords. And now onwards, okay, now if you've done it, you've done everything, you checked and you have gotten all the answers, remember to go back and read through the question again and your answer again to identify where are the mistakes, where are your gaps in your revision. Then before you move on to the next paper, remember to touch up your gap, bridge your gap. Okay, make sure that your whatever mistake you have made in this paper, it does not appear in the next paper again. Okay, this is what we mean by effective revision. Okay, making use of this past year paper not just as a platform to see more questions. It can also serve as a platform for myself to actually reflect on my understanding, my revisions, and my missing my keywords. Okay, so that you will tell me which area is I'm weak at, and which area that I actually should be improving on. Then after that, I use that as information to improve myself, and I want to challenge it. So I'll in the next paper, to discover more gaps or to see how solid is my revision and how solid is my understanding of the new materials that I actually memorize or actually understand. Okay, with that, okay, same thing as before. If you would like to get updated, the latest update notification for my papers, okay, or my notes, okay, remember, okay, to subscribe to my channel and to actually press the bell button, okay, so that you will be notified of any updates or any latest video that I have uploaded to my channel. Okay, if not, okay, see you in the next video of Papa Lim Physics Classroom. Okay, thank you. Bye-bye.